Oxidation reduction reactions occur a lot more often in chemistry than we think. Generally, we say oxidation reduction chemistry is a section in a general chemistry textbook. We never really have to worry about it ever again once we pass through electrochemistry. It's not really the case. When I'm talking about oxidation reduction reactions, we have another name for them, by the way, and that other name of them is called the redox reactions. We have reduction and you have oxidation, so they call them redox in a short term, right? But in reality, what happens in these systems is a transfer of electrons. So oxidation reduction or redox reactions is a transfer of electrons from one atom to another, okay? And generally what we end up seeing this with is we end up seeing this with a lot of metals, right? This is especially true whenever we're talking about electrochemistry. For example, if I have zinc solid and copper ion in solution, what ends up happening is that the zinc is going to lose 2 electrons, and what I'm going to end up with is a zinc 2 plus ion and copper solid. Now if you notice that the copper here is a plus, right, and the zinc over here is 2 plus, that means the zinc is losing 2 electrons. So I've got to have 2 coppers here, right, to balance my overall redox system. Excuse me. Now, what we like to do when we're dealing with these systems is break them down to 2 different systems. So let's see what's happening in the 2 different systems, and we're going to label these things as half cells. So my first half cell is going to involve zinc, right? So zinc solid goes to zinc 2 plus, and at this point, because this was neutral, I have to balance the charges on the system. So now I get 2 electrons out. All right? My second system that I'm going to use is copper. All right? And in this case, it took copper plus, and it's gaining an electron to become copper solid. All right? You have to make sure that the electron's balanced, so I'm going to have to multiply everything in here by 2, because you can't have free electrons flowing around. So we want to make sure that the electrons on the left with the copper and on the right with the zinc are both equal. So now I've got this particular system. Which one is going to be oxidation and which one's going to be reduction? Now I haven't defined those yet because I want to show you an example, then define them. In the top reaction here, did the zinc lose electrons or did it gain electrons in that half reaction? It lost electrons, okay? Down here with the green, what happened there? The copper gained electrons, right? In these 2 cases, we have oxidation when we lose electrons, right? Okay, so oxidation, we lost electrons, and for gaining electrons, it's a reduction. Okay, now I'm going to show you a mnemonic to try to see you remember this. Oxidation lost. So I'm going to say oxidation is lost electrons. So notice that becomes, we don't include the S there, that becomes oil. Okay? Oil. And over here, reduction is gain. Rig. All right? Oil rig. Oxidation is loss, reduction is gain. That's one way of remembering the system. Another way of thinking about it, and it's a little bit more colorful of a way, is to think about a lion Alright, there's a lion, okay? It's a really bad lion, we'll put whiskers on him. There you go, there's your lion for you. Alright? Leo the lion says grr. Alright? Loss, you lose electrons, you oxidize. Gain electrons, you reduce. So if you see Leo the lion, Leo says grr. Lose electrons, oxidize, gain electrons, reduce. Two mnemonics that might help you remember which one of these things is an oxidation and which one of these things is going to be a reduction. Okay? Alright, so this is a very simplified system. I want to talk about this with a little bit more detail, especially when we get into things that where we're determining oxidation numbers on more complex systems. Because the oxidation numbers that we have for both of these, for zinc it's 0, it's our oxidation number, it's a charge, right? And over here it's +2. For copper over here it's +1, oxidation number over here is 0. Okay? Those are easy oxidation numbers to determine. A lot of times the oxidation number is not going to be so clear cut. So let's look at some rules and then determine some oxidation numbers in a variety of different compounds. So let's start by defining the rules of oxidation reduction. Okay? There's a couple of basic rules, right? For the most part, if you have H and it's bound to nonmetals, the oxidation value of that H is going to be +1. Okay? If you have an H that's bound to metals, its oxidation value is going to be -1. Okay? If I have an oxygen, in general, if an oxygen is there, it's not attached to another oxygen, it's going to be a -2. Right? When you get to fluorine, fluorine is always going to be a -1 oxidation number. And for chlorine, bromine, and iodine, usually these are going to be -1 as well. The only time they're not is when you have oxygen or fluorine bound directly to them, in which case their oxidation number changes. Okay? If I have a metal, okay, if I have a metal, like lithium, sodium, or potassium, generally these things are going to have an oxidation number of +1. Okay? Now when I get into compounds, I have to look at compounds and I have to try to figure out what their oxidation number is. And it depends on how they're represented. Okay? I'm going to represent this two ways. The first one is KMnO4, and the second one is going to be MnO4 with a -1 charge. We have to figure out what the oxidation number on the manganese is going to be. Okay? And we can do that using these rules to determine the oxidation value of the metal. Now what's the overall charge of KMnO4? It's 0, right? So after I add all these things up, my overall value is going to be 0. So first I have to look at this, and I've got K up here. So I've got potassium. Now look over here at my rules. So I get a +1 value for my potassium. Now I'm going to look at my oxygens. Oxygen is -2. Okay? And I've got 4 of them. Okay? Right, so what is my current value? So you add that up in your head. Plus 1 minus 8. So whatever number is there, I've got to make sure that it gets me to a 0 value. The only atom that I haven't dealt with yet is manganese. So I'll write manganese here, and what's its overall value got to be in order to get to 0? That's right, plus 7. Okay? 7, 8, and then minus 8. It's going to be 0 total. Okay? Now, if I look at permanganate as an ion, it's a very similar way of doing things. Except over here, I'm using a minus 1. This charge value is going to be my target for figuring out what the ion, or excuse me, what the oxidation number is going to be of manganese. And in this case, all I've got, I'm just going to do 4 times oxygen here. So that gives me a minus 8. Because oxygen's minus 2, multiply that by 4, it's minus 8. Okay, so I'll put minus 2 here. That's why we get minus 8. So now all I have left is manganese. And in order to get to minus 1, what's the value on manganese going to be? That's right, plus 7. Okay? So those are my two values. That's how I get to a minus 1 using permanganate. All right? You have some questions on this? Well, let's do another, and we'll see how that works out. All right, here I have dichromate, and I've got carbonate as my two ions. Okay? So, how am I going to figure out what the oxidation numbers of both these are? I've given you some examples now, and we've got rules here. So why don't you pause the video right now and see if you can solve these things. And I'll solve them, and you'll see if you're right. Okay? So, our overall value here is going to be a minus 2. Okay? Now, I've only got 2 atoms. I've got the oxygens and the chromate. Now, I know over here in my table, oxygen's minus 2. So, I take oxygen and multiply it by 7. That's a minus 2 times 7, by the way. So that's going to be equal to minus 14. Okay? But now at this point, I've got 2 chromates. So how am I going to resolve the 2 chromates? So I've got Cr times 2. But I don't know what chromate is. So how am I going to resolve that? Well, this is going to be 2x, right? And if you look at this, you're like, well, this is 14, this is minus 2, so I'm going to need a plus 12 in order to get there. So what's x going to be? That's right, it's 6. So this plus 12 is because the chromate here has to be 6 in order to get to my plus 12, because I've got 2 chromates there. So the oxidation number for chromate is going to be a plus 6. Okay? What about for carbon? What's the oxidation number for that one? My overall charge for carbonate is a minus 2. I've got 3 oxygens here, so oxygen times 3 is going to be equal to minus 6, because each one of these is a minus 2. Right? Which means that the carbon has to be equal to something that gives me a minus 2. So that gives me a plus 4. Okay? Good. A few more examples. Okay, now if we look at methane, which is CH4, the overall charge of this thing is 0, because I have a 0 charge up here. Okay, and I'm looking for what the oxidation number of that carbon is going to be. Remember in the last example with carbonate, it was minus 4. But in this case, I have a hydrogen bound to a nonmetal, that nonmetal being carbon. So if I have 4 times plus 1, this is the hydrogen, that gives me a value of plus 4. So what's carbon's value got to be as far as oxidation numbers in order to get me to a 0? That's right, minus 4. So the oxidation number of carbon in this molecule is minus 4. Now what about over there for aluminum? In this case, I've got a minus 1 as far as the charge goes, and I've got 4 hydrogens attached to an aluminum. Aluminum is not a nonmetal. Okay, so the double negative means that it's a metal. So that means my hydrogens have to be hydrides. They've got to have a -1 charge. So in this case, I've got 4 times H, in this case, or 4 times -1, and that's going to be equal to -4. So the charge in aluminum is what we expect it to be. Aluminum is going to be a +3 in order to get me to that charge. So aluminum hydride has a -1 charge. All the hydrogens have -1 charges there. Okay? Hopefully you're good with oxidation reduction reactions.